Hello, today we're going to talk about topic 2, section 10, scaling using logarithms and linearizing the data. Okay, we want to linearize the data means we want to try and make the data make a straight line. Okay, if we can make our data fit a straight line, then we can do all that fun stat stuff, right? So we do that by scaling our data. So for instance, here we have our objects and then their size, okay? So we have very different sizes, very small, very large. Well, instead of comparing these numbers that have such a vast difference, we can take the natural log of every single number. So taking this natural log, now our range is significantly different, okay? We're talking, now we're going just major difference, right? So let's do an example. So here we have our time in hours and bacteria growth. Okay, so how much has the cells increased by? So first glance, when we just do a scatter plot of the data we're given here, it's not a line. Okay, it's exponential. It's just definitely not a line, and that's what we're trying to do. We want to make a line. So let's change it by taking the natural log of these massive numbers, right? This big old change. So the number of cells. So now when we do that, the numbers are a lot closer together, and now we can compare them here, and now we can get more of a line. Okay. This is called linearization, okay? Z is the American way to write it, and the European way is with an S, okay? So you'll see that incognity written like that. All right, so here we have our function, okay? So notice what this came from. The right-hand side is that line. So when we found this scatter plot and we use our calculators to get this equation, all right, that's not really the equation of the original data, right? If I want to go back and plug in original data, then I need to change it. So I need to change my y is not y, it's the natural log of n. So that's why the answer is written, or the formula is written like this. Now, typically, if we want to graph it, we can't put the natural log of y, it has to be y equals, so we rewrite this in exponential form. So this is now e to the 0.242x plus 3.76. And then we can even change this even more, all right, with this addition. We can write it as e to the 0.242x times e to the 3.76, and that's a coefficient, right? It's out in front. We can think of it like that because it's just a number, right? There's no variable here. Okay, it's just another way of writing it. So this is we can linearize this data, and it turns it into an exponential function. Okay, essentially, we take the natural log of the y. So now let's do example 2. So now we're going to look at that box office data set from Frozen 2, excuse me. So here we have the weeks and the total gross. So numbers are pretty huge. So let's take the log of that. Okay, so we're going to take the natural log. Wait a second. What am I doing? Oh, sorry, we're doing the natural log of x. Okay. So instead of doing the natural log of y, of these really, really big numbers, what happens if we take the natural log of the x's? Okay, sorry, I forgot which problem we were on. So on this one, we do the natural log of the x's. So here now we can see we can get a line, all right, which is great. So we plug that into our calculator, we get this wonderful equation. However, that's not the original one, because the original one, x is the natural log of w, and our y came from our g. So if we replace those, we get, hold on, I'm getting there, natural log of w plus 2, 1, 3, 1, 8, 6, 7, 5, 7. Okay? So see how we're replacing our y and our x? And notice that's what happened. Well, I guess I didn't. I guess I wasted all that time writing that out. I didn't really need to. Sometimes I forget what I have already typed out until I uncover it. Okay, so our y is really g, according to our data, and then x is really the natural log of w. So make sure you're putting in the correct variables in your final equation. All right, so wow, I kind of spoke real fast there. Sorry about that. Let me recap. Example 1, we had more of an exponential growth. So we took the natural log of y. All right, example 2 had more of a log growth, right? It started to slow down in its growth. So we took the natural log of x. Okay, I didn't really explain that very well. So if you have an exponential growth, take the natural log of y. If you have a log growth, then you should take the natural log of x. Okay. When you do this one, you end up with an exponential function. Okay. When you do this one, you end up with a natural log function. Okay. This is how we can convert our data and get our equations. All right. So then if we took the natural log of both x and y, this models a power law relationship. All right. I'll show you what that one is next. Okay. But that's when we end up taking when we do both of them. So, knowing the definitions, a semi-log model would be used for exponential and logarithmic functions. Logarithmic relationships. All right, a log-log model would be used for power law. Okay, semi-log, where only one thing is being taken the log of. Log-log, both of them are taken the log of, right? Kind of makes sense. So let's do a power law. So here you can see we've got large numbers in our data. So here it might benefit to the natural log of both of them. So if we take the natural log of both, we get a fairly linear, relationship. I mean, that's ideal, right? Look at that, how nice that one is. All right, so we graph it, we get our linear equation. Now to get our actual function, right, to do an approximation here, well, our x is now the natural log of d, and our y is the natural log of p. So when we replace those, we get this, which is kind of gross. Oh, I don't know why I put x. I meant to put the natural log of d. Oh, I put that one in the wrong spot. Silly me. Okay. Trying to watch my mistakes now. I know you guys are looking for them. All right. Just kidding. All right, so here we have this equation. I don't like all the natural logs, right? I want to get rid of it. So what can I do? I can put it in exponential. So then we get p equals e to all of this. Beautiful. Okay, and I don't like this minus part. So instead of putting it up here, I'm just going to put a division and get e to the 1.605784, right? Because when you subtract exponents, you're dividing them, okay? So, all right, I'm getting closer because now I got a constant. All right, let's clean this up some more. If I move this as an exponent of d, well, remember, e to the natural log of, I want some, like w, is just w, right? That base, if that base and this base are the same, they kind of cancel each other out. Hopefully you remember that rule. So if we do that, then we can get this e and that natural log to cancel. So then, well, what I've really got, if I can rewrite this, as e to the negative 1.605784 times, well, d to the 1.49879995. All right, so let's see what we got. I don't know why I wrote it like that. Yeah, it's not going to let me move it. All right, let's see what I get. Okay, which is the same thing we got here. All right, the only difference is this is my exact answer. Okay, well, from, I guess this was a rounded answer anyway, so I guess I should go ahead and rewrite this coefficient is the same thing as that, so put in calculator. And then here in rounded, we get this. Okay, so our approximate graph. All right, for the original function, this is what we should do. So I'm sorry, I circled this. I meant the original values. We can use this equation to model it. Okay? Hopefully that makes sense. Knowing how to take the log of variables and scale it, and then get your line. All right.